Hello everyone, and welcome to the official YouTube channel for Wayne State University's chapter of the Tau Beta Pi Engineering Honor Society. My name is Austin Heitzman. I am back again with another linear algebra tutorial video. Today we're going to be continuing with chapter 2, covering now section 2, which is linear combinations. If there are some material from chapter 1, things like matrix equations or multiplication that you're not quite familiar with, I highly recommend you going back and checking out those videos, which are also posted on our channel. It will be pretty helpful for understanding this material. So without further ado, let us begin. So to start about talking about linear combinations, I first want to look at coordinate vectors, right? So there are three basic vectors in R3, right? So in basically three-dimensional space, these vectors are going to be representing like the graphical axes, right? So if you have like a 3D graph, you have three axes, right? X, Y, and Z. And since vectors can be represented graphically, like it's going to be important to be able to represent like the axes, right? So if we think about like the x-axis having just an x component and the rest are zeros, or the y-axis doing the same, just the middle component being some number and the rest being zero, and same with the z-axis, we can kind of translate this to a vector form, right? So we're going to label this like E1, E2, and E3, but you can kind of think of this as like E1 being like the X, E2 being Y, and E3 being Z. So in that regard, E1 is going to be the vector 1, 0, 0. E2 is going to be 0, 1, 0. And E3, 0, 0, 1. And this is pretty familiar if you've ever taken like Calculus 3 or like a physics class. This kind of is very reminiscent of like the I hat, J hat, K hat, right? Which is pretty much exactly these vectors, if you remember. 1, 0, 0 for the I hat, 0, 1, 0 for J, and 0, 0, 1 for K. If you haven't taken those classes, you can completely ignore that. It's not very relevant here, but it's good to like kind of ground yourselves in something if you do already have that background knowledge. So what's cool about these specific unit basis vectors is that any vector we possibly have can be written in these terms, right? How, you ask? Well, let's look at something concrete. Say we have a vector v, and its x component is 3, its y component is 5, and its z component is 6, right? Well, since we know that we can use scalar multiplication and addition to represent this vector, we could basically look at this as pulling this out and then just writing each component of these unit vectors, right? So for the x component, we can have 3 out in the front and have 1, 0, 0, plus 5, 0, 1, 0, plus 6, 0, 0, 1, right? And we know, based on what we've worked on in chapter 1, that this is basically like the 3 here is going to distribute into here, get multiplied into each component, so that would be 3, 0, 0, and then same with the 5, 0, 5, 0, and then same with the 6, the z term would be 0, 0, 6, which is all going to stack up since we're adding it, and it's going to equal that 3, 5, 6, right? So in this case, we can say that V is a combination of E1, E2, and E3. And like I said, literally any vector you can possibly think of can be a combination of these standard vectors right here, right? That is not to say, however, that these vectors are the only ones in the world that can form linear combinations, right? There are others, and it just depends on the problem. But before we go into that, we need to like actually define what a linear combination is, right? So, basically a vector can be written as a combination of other vectors using addition and scalar multiplication, right? And if that's true, then this vector is a linear combination of the other ones in question, right? And that's exactly what we saw up here, right? I mean, we took 3, 5, 6, and we wrote it as a combination of scalar multiplication and addition of E1, E2, and E3. And that's pretty much the ballgame. I mean, that's what we're doing, right? Like I said, however, like it's not always just E1, E2, and E3. Oftentimes you're going to get problems and it asks you if we can like form a combination of some certain vectors. So in order to solve those, we need to know how to check for it, right? And a lot of this procedure is going to seem really familiar if you were paying attention during like bringing matrices to row echelon form, for example. So if not, again, check those videos. We have them posted. But if you feel like you're ready, let us dive. So I'm going to write out the steps like in words, so then off to the side we can kind of sketch out like what a really brief, simple example would look like. So the first thing you're going to do is say that you're given like a set of vectors v, v1, v2, just for example. That's a comma, not a 1. So the first thing you need to do is basically line up all vectors as an augmented matrix. Which, as you remember, is sort of that like matrix with the arguments on one side, and then we have that line that separates the solutions. You remember that. You guys are smart cookies. You know what's going on. Okay, so after we've done that, we are going to want to bring the augmented matrix to reduced row echelon form. We have a whole video on that as well if you need a refresher. And from there, once you have this in reduced row echelon form, you will be able to analyze the result for inconsistencies. So the basic rule of thumb is if inconsistent, answer is no. Not a combination. But if it is consistent, the set is a combination. And in order to fully answer the question, the set is a combination, and then the solution vector gives the scalar multiples. So let's just like really quickly off to the side like sketch out what this means, because like this is a lot of words, right? But let's say we have like v as a solution vector, right? Let's say that that is like -1, 1, and 10, right? And say we have v1 is equal to 1, 0, 1, v2 as -2, 3, -2. We'll throw one more in there as well. Give us v3. It's -6, 7, and 5. Well, remembering what we just defined a combination as, basically what we want to answer here is, do scalars C1, C2, and C3 exist such that C1 times V1 plus C2 times V2 plus C3 times V3 equals V, right? And that's essentially, again, exactly what we did up here, right? I mean, in this case, C1 is 3, and V1 is E1. C2 is 5, V2 is E2, right? And C3 is 6, and E3 is V3, right? And all of those can add up in a combination to form this vector here, right? So that's essentially all we're doing. The numbers just look a little bit different than those really basic like zeros and ones, right? So I'm not going to do like this full example, but just so you can see like how to set this up. In order to answer this, well, we're trying to find if there is some number for each of these vectors, right? And we can think about these C1, C2s, and C3s. We can think about these scalars as if they were like X, Y, and Z, right? If it helps you to call C1 X, C2 Y, and C3 Z, well, by golly, we've seen this before, right? I mean, this looks really similar to a system, right? At that point, we can break all of this down so that each of these numbers are being multiplied by these variables, and now we just have like a basic like linear system of equations, right? And knowing that, we can stick all of that into an augmented matrix, right? So the way I would do that for this, again, we're not going to go all the way down to like reduced row echelon and solving it, because we will do an example like that later, and also y'all know how to do that. I believe in you. But in this case, that first vector would be the first column of the matrix. The second vector is the second column of the matrix. And the third vector is the third column of the matrix. And then this V right here, well, we're seeing if this is a solution to this. So V is going to be on that solution side of the augmented matrix. Now I encourage you to try this problem just like to see if you kind of get the gist, but basically the idea is once we do take this down to reduced row echelon form, well, if you'll remember from chapter 1, when we do that, when we manipulate this side, we also have to change this side, right? So if we can get it so that this is 1, this is 1, and this is 1, and the rest of them are zeros, and each of these is a non-zero solution, right? In that case, then whatever these numbers are going to be, well, this top one is going to correspond with C1, this middle one is going to correspond to C2, and this last one is going to correspond to C3, and that is going to be the scalars that will make this work, right? That was very wordy, I know, but I hope just kind of putting it that way might help you see this a little bit easier. This was definitely a concept that like took me a minute to get stuck in my brain, so yeah, we'll do an example in just a second, but before then, I just want to briefly look at vector form of an equation, which is going to take us basically to like a different way of doing matrix multiplication, which is honestly like kind of easier to think about than what we have worked with before. So if you'll remember from chapter 1, the matrix form of an equation is that AX equals B, right? Where A was some matrix and X was like the X, Y, and Z, and B was like the solution, right? Well, in order to get to vector form, there's a question I want to pose. Basically, what happens when we break this matrix A up into column vectors, right? So like basically if A from above was like 1, 2, 3, 1, 2, 3, 1, 2, 3, we can break that up into column vectors. It's like 1, 1, 1, 2, 2, 2, 3, 3, 3, right? It's like this is one column, and this is one column, and this is one column. Like they all just get their own vector space, right? And when we do that, it's, I would say, a very simple way of kind of putting this into vector form, like what we were just seeing, right? So if we look at the matrix in terms of vectors, then we can rewrite this, right? Since, say, the x variable is going to be multiplied by everything in this first column, and the y variable by everything in the second column, and the z variable by everything in the third column, and that is all going to equal the respective solutions, right? Well, we can essentially write x times a11, a21, a31. We're just going to keep this in 3 space right now, but it does apply to any space. Plus y, a12, a22, a32, plus z, a13, a23, a33. And that's just going to equal the b1, b2, b3. So what have we done? We just wrote this matrix as a linear combination, right? It's the same dang thing. Now, what does that mean? Well, this basically, we were using that as multiplication, right? I mean, you know, and it was like a long, lengthy process of taking dot products and everything. But what this is saying is that this matrix can just be written down as a linear combination. So we can essentially use linear combinations to think about matrix multiplication, which is pretty cool. Now in practice, I will say, like, it's generally on the fly. It's just going to be easier to take the dot product like we did in chapter 1. However, conceptually, it is pretty good to keep in the back of your mind. Like, basically all you're doing is just breaking it up into a vector combination, right? So that's pretty neat. Some of these things are kind of starting to come to a head and come together in ways that maybe we didn't realize at the beginning, which is, for me at least, like one of the most rewarding things about a class like this. So now that we have all of the terminology under our belt, let's actually focus on an example. Instead of just starting one out and kind of going through words, let's really actually do one of these, right? So the one that I chose is to determine whether this set is a linear combination. And again, when they ask that, you're basically saying, is there a set of scalars that can be multiplied by these guys and added together so that we get this, right? So our first step, if you remember, is to put this in augmented matrix. And here you remember the first vector is the first column, second vector is the second column, and third vector is the third column. And then we're going to augment it so that this v can be represented as the potential solution. Right? Hopefully everybody can see how we got that. And now the second step, everybody's favorite step, reduced row echelon form. Yay! So let us, it will go medium speed. How's that? So looking at this, I think the first thing that I can do, we can use this 1 as a pivot point, right? So that we have -2 r1 plus r2. It's going to give us the new r2. And row 1 plus row 3 is the new row 3. And if this seems like I'm speaking a different language to you, again, go back to chapter 1 and review all of this really quick, because it does not stop. It's going to give us a 0 here, we have 2 minus 1 is 1, and 0 plus 1 is 1. And then we need to do that same thing in the solution column, right? Because that's how we're going to get those scalars if they exist. Negative 2 times negative 1 is 2, plus 1 is 3. And for this, should be simpler, right? Okay, so the third step, I want to use this as a pivot and eliminate these guys, right? I could do that by doing negative 2r2 plus r3 is the new r3. And this, you can already see that there's something fishy going on, right? Since these two are the same. That's going to give us negative 6 plus 4 is negative 2. Now this is inconsistent, right? There is no earthly way, unless we completely redefine what 0 means, that all of these zeros can somehow equal a negative 2, right? You cannot have any sort of variable that, you know, is 0 on one side and negative 2 on the other. 0 never equals negative 2. Therefore, this is not a linear combination. And in such case, this has become pretty easy, right? We're kind of, you know, off the hook from actually solving anything further than that. However, for the sake of tutorial, I do just kind of want to demonstrate like what it would look like, right? So I'm just gonna like invent a new matrix. I'm just gonna make a really quick little change. I'm gonna change that 0 to a 1, right? Purely for educational purposes. We're doing this on the fly too, so let's see if this actually works. Well, now this is something that we can take into row echelon form, right? At that point, we can use this to get rid of this 1 right here. What step was I on 3? You can do negative row 3 plus row 2 goes to row 2. And then we also want to get rid of this guy. And technically, I mean, you don't really need to take it all the way down to reduced row. I mean, at this point, you can be able to figure out pretty quickly like what each of these scalars should be. However, it is even faster if you have everything in reduced row echelon form, so I tend to like doing that. We could just do r2 plus r1. It's going to be the new r1. It's going to give us 0, 0, 1 on the bottom, 0, 1, 0 in the middle, and 1, 0, 0 at the top. Now, this is in reduced row echelon form. We have our diagonal of 1s and everything else is 0. And at this point, we do have a valid solution set, right? So in this case, if this were our original problem, it would be a combination. And remember, like, basically what we're asking if is like the C1, C2, and C3 exist such that C1 times V1 plus C2 times V2 plus C3 times V3 equals V. I know I already said that, but again, like, the more that you actually put this into context, you know, the more you actually remind yourself that's what we're doing here, the faster that this is going to click for you, right? And in this case, Well, yes, it does, because if this row is this column is C1, and then this column is C2, and this column is C3, well, when C1 equals 1 and everything else is 0, then this is 4, C2 is 5, and C3 is negative 2. So in this case, sorry about that, we can list our answer. C1 equals 4, C2 equals 5, and C3 equals negative 2. And that is essentially like the final answer that they're actually going to want from you if such a combination exists. Again, that is not the correct answer to the problem we started with. I changed things just for demonstration purposes. But I did want you guys to see what it looked like in either case. So, this has been fun, a lot of new information. And the next section is full of even more. I'm super excited to share it with you guys. We're getting to the fun stuff now. In order to get a notification when that posts, please remember to subscribe to this channel. I will have plenty more linear algebra videos coming up in the near future. Additionally, we have all sorts of other tutors offering videos on all sorts of other STEM subjects. There's other math courses, there's chemistry, engineering, anything you can think of STEM related. So be sure to check those out if you have trouble in some other classes. And in the meantime, I hope you have a fun time learning. See you next time.